All right, guys, today we're going to look at section 6.4, which is on arc length and surface of revolutions. And let's get right to arc length. In fact, before we do anything with arc length, so let's say that we have some curve here that does, I don't know, some weird thing like this, but it's a nice smooth differentiable curve. And let's say that we know that it starts here and it ends here, okay? And so let's say that that's A, and then let's say that over there is B. And I want to know the length of the curve. That is what we call the arc length, okay? It doesn't have to be a circle, because every time in the past, whenever you've heard the word arc, you think of circle or trig or something like that. It's the arc. In fact, in the book, they do an arc length. I think even on my video, I do the arc length of a straight line segment, which isn't very interesting, but when you work it out, guess what it turns out to be? The distance formula, which is something you know from Algebra 1. Anyways, so here is the formula for the arc length when we're doing it with respect to the x-axis. Arc length, S, is equal to the integral from A to B, so you would start at A, you would end at B, and it turns out it's the square root of 1 plus, then you have to find the derivative of the function, and then take that quantity squared dx. Notice that I did not write d squared dx like this. What's that mean? That's second derivative. That is not, in general, that is not the same thing as f prime of x squared. You guys get that, right? So anyways, if you're doing it with respect to the y-axis, then it would be the very similar formula just with y's. Now, if you're interested in where this formula comes from, I'll give you a hint. It has something to do with the distance formula. We just mentioned it. But more importantly, I posted a video on the module. The very first video shows you where it comes from. But if you don't care where it comes from, then I would just say know how to use the formula. By the way, you will have to have this memorized in the future, so you need to know it. So here's a lovely problem. It says calculate the exact length of the curve y equals 4 radical 2 over 3 x to the 3 halves minus 1 from 0 to 1. Oh boy. In other words, we are trying to find the exact length of the curve from here, let's call that A, to 1, which would be here. Let's call that B. What is that length? Now, if you look at it, if we did the actual linear measurement between those 2 points, it actually is very close to that, right? But it is not exactly the same. We're going to find the exact length. Okay, so now we got to show some work here. All right, so first of all, we know what y is, and in our formula, in fact, let's just start with that. The formula is the integral from a to b, square root of 1 plus whatever f prime is, squared dx. Agreed? So what are we going to need to find? We need to find f prime, right? So let's do that first. We're going to do that in purple. All right, so y prime. Okay, so that's going to be 4 radical 2 over 3 times 3 over 2 x to the, well, that'd be 3 over 2 minus 1, whatever that is, correct? All right, so let's clean that up. So y prime is going to be equal to, well, let's see, those 3's would cancel, that 2 would cancel that 2. So I think it's 2 radical 2 x to the, I think that'd be 1/2. Or I guess you could even write that as 2 radical, fix that. Two x, all underneath that radical. In fact, if you wanted to, if you really wanted to get interesting here, we could say that f prime, which is equal to y prime, is equal to the square root of 8x, couldn't you? Right? And it seems really unintuitive or unnatural to do that, but you'll see what are we going to do with that thing? We're going to square it. You don't have to do this, but I just did it when I was working out. So, okay, so let's go ahead and proceed. So the arc length, S, is going to be equal to, well, I think we're going from 0 to 1 if I'm not mistaken, aren't we? So then we're going to do the square root of 1 plus, and I'll do that back in purple. So now I'm going to have the square root of 8x squared dx. I'm recording here. Good. All right. So that's going to be the integral from 0 to 1 of the square root of 1 plus 8x dx. Now what? U sub. U sub. There we go. U sub. Alex, U sub.
U sub.
Thank you. Thank you. We got to get a little bit of excitement here. Okay, so we're going to do some U sub. This isn't too bad of a problem, is it? We're going to do a little U sub. Okay, so we're going to do some U substitution, our favorite substitution method, and probably the most useful one of all of them. So what's U going to be? Well, it's going to be 1 plus 8x, I think. What would du be? Well, it'd be 8 dx, but there's no 8 here. So we're going to divide that 8 over to the other side. So that'll be 1/8 du equals dx. Also, I would like to know, I'm not sure if I've got extra room. I don't. Okay, so I'm going to have to try to squeeze all of this in here. Also, I would like to note that 0 will change to what? What will this 0 here change to? 1. You plug 0 into this, and you'll get 1. Does that make sense? So what I'm doing is I'm converting my entire integral into U. Oh, wow, that sounded clever, like you'd say that to someone. Okay, anyways, what does 1 change to? 9. Okay, so now we can go ahead and let's go ahead and do it in green. So this is going to become, I think there's a 1/8 in the front, right? 0 is changing to 1. 1 is changing to 9. And then I've got u to the 1/2 power du. And let's go and integrate. So that's going to be 1/8. The antiderivative of u to the 1/2 would be u to the, I think that'd be 3/2, right? Then divide by 3/2, which is the same thing as multiplying by 2/3. And then we've got to evaluate that guy from 1 to 9. So is that 1/12? 1/12 times 9 to the 3/2 minus 1 to the 3/2. Square root of 9 is 3. To the third is 27. So 27 minus 1 is 26. So you get 26 over 12 or 13 over 6, I think. Yes, looks good. So the exact length of this curve from here to here is 13 over 6. So really, this arc length thing isn't really that difficult. You've got to know the formula and then just be able to integrate. Now, obviously, if this was a graphing calculator problem, you would just, at this point right here, I would just plug it in my calculator. Now, I'd probably simplify that a little bit. I mean, I could do that and get to this. But if it's graphing calculator, feel free to just use your calculator. If it's not graphing calculator, then obviously you got to try to crank it out by hand. And they're probably going to try to give you numbers that are easy to find values to. Comments or questions on arc length? Do you think that would have been too much to see last year? I don't think it's tremendously difficult. The challenge is remembering the formula, which is not a difficult formula. But, I mean, if we go back to the warm-up, if you think about the washer method, is that a hard formula to remember? Not really. But maybe back last year, maybe you thought it was hard. I don't know. Okay, so it's all relative. All right, so let's do the second part, which is the area. It's basically just surface area. So if we think about like a semicircle, right? So let's say I had some graph like this, and let's say I had a semicircle with center of 0 like this, and then let's say I wanted to rotate that around the x-axis. Of course, that's going to make what shape? It's going to make a sphere, right? Sphere. And if we were doing the warm-up, the volume of revolution, that's exactly what you do. You do pi r squared and get your answer using the disk method, correct? Now we're not looking for the volume, though. We're just looking for the surface area. We're looking for the surface. So we would just want to know what is the surface area of that thing that we rotated around the x-axis. Now this formula looks a little bit harder. Now you'll notice that there are some similarities with this guy here and this guy here, right? What does that look like? Well, that looks like our arc length formula, correct? By the way, what is the formula for well, we're talking about rotating it, right? Does anybody remember this formula by chance? What is that formula? Circumference. So now instead of doing pi r squared, which would give us the volume, right? Because we would do the complete disk, we're only really interested on the outer edge of that rotation, correct? Does that make sense? So if you think about it that way, now by the way, you might say, well, Mr. Allen, you didn't really show us where the arc length formula came from. I know, I saved that lovely video for you, right? But it's kind of intuitive here, right? This gives me the arc length. This gives me the circumference. Okay. Oh, does anybody want to take a gander or a guess why that's R? Versus why doesn't it say f of x there? You want to take it? You got it. You remember the big R and little r we were talking about? You can have some curve that's drawn like here that's rotating around the x-axis, correct? But what if I said rotated around the line y equals -4? Well, r is going to change then, isn't it? Does that make sense? We'll talk about that in this example. All right, now this is not a semicircle, okay? This is a parabola, which is not a semicircle. It says find the area of the surface formed by revolving. In fact, actually, let me just, can you guys go ahead and just see if you can set this up? Here's a formula right here. We're going to use this one. We're doing it with x. In fact, let me erase all this other stuff I put on here. So erase all of that stuff. There's the formula. Just see if you can set this one up. And you're probably going to run into a bump or two, but then we can talk about it. We're going from 0 to 3. Okay, let's go ahead and fill in what we know. All right. By the way, this is a big S. The first one was a little s. Okay. 2 pi is just 2 pi, no big deal there, right? Okay, what's A? 0. Super easy, right? That's 0. What's B? 3. No problem there, Mr. Allen. Anyone can figure that out. Okay. What's R of x? What is this? What is R? It's just the function g of x. In fact, I'm going to write it out explicitly, right? And I'll do this. Yeah, let's do it in red. So this is just going to be in parentheses 3x minus x squared. But if you wrote g of x, you wouldn't be wrong. You're right. They're equivalent, right? Now I've got to do the square root. Let's do that in purple. I've got to do the square root of 1 plus. Now, what is the derivative of g? I hope you can do that in your head. What is the derivative of g? 3 minus 2x, right? So then in here, I'm going to do 3 minus 2x. But then what do I got to do with that? You will have to square that. And then, of course, you got your dx on the end, and I'm kind of off the edge there. But if you, how many of you got that set up on your own? Ta-da! Oh, by the way, guess what we're going to do on this one? Let's go and use let's practice our calculator now. Let's not do this one by hand. I want you to go ahead and use your graphing calculator to get this answer. Make sure actually, it doesn't matter here if you're in radians or not. I'm going to pause the video. Anybody got an answer? 44.877. I agree. Was that too bad? That's the lesson. That's basically it. I just have one more question for you. First of all, does anyone remember this is the surface area generated when we take that curve, that parabola, and wrap it around the x-axis, do a full rotation of that. Does anyone have any questions on how any of that came out? Really a pretty easy section, I think. Easy section. Okay. My last question is this. How would that problem, that last problem we did, how would that have changed if we revolved it around the line y equals -2? I want you to just write what you think, write the formula with how you think that would change if instead of revolving it around the x-axis, I had you revolve it around the line y equals -2. How would that change? How would that have changed it? All right, so our original problem was big S equals 2 pi r integral from 0 to 3, correct? What's the only thing that changes in this example? The r. What will r be in this example?
3x minus x squared plus 2.
Correct. This was what, 3 minus 2x, right? Please make sure I wrote that correctly. Did I get everything written correctly? Does that look okay? And we can figure out what that is. I don't really care. Just note that this r, it's essentially the same problem. It's just now we've got this curve here like this, and we're rotating it around this line down here, y equals -2. So our r is now, remember, I do top minus bottom. So you would have done 3x minus x squared minus -2, which is where you get the +2 that he mentioned. Okay? Questions? All right, guys.